All right, so this is our intro into converging and diverging series. So before we do that, we got to go over what our partial sum and infinite series are. So our partial sums are just our sums. So if we want a sum of the first term or the first two or first three or first four or the first n, that's the notation we're going to be using it. So S sub 4 would be the sum of the first 4. S sub n is the sum of the first n. Now for an infinite series, we're going to continue this n on to infinity. So we can write it this way, or we can put a limit as n approaches infinity in front of it, which is the one I like. And so if you think about all those terms being added up, we can just say it's the limit as n approaches infinity of our partial sum. So if this partial sum goes off to some letter s, we say that it is convergent, and that limit exists and is finite. If it doesn't, we say it's divergent. So what we're going to be doing is looking at these partial sums as they go off to infinity first to determine if they're convergent or divergent. And there will be tests and other tricks and stuff that I will show you in other videos. But this, again, is just an introduction to it. So we're going to look at Desmos for the first one. This is our first, and you can see there's our infinite now. And it basically is this. I've already got it plugged in here, and all you're doing is you're hitting play. So our n here is going off to infinity. So we're trying to see what is that sum approaching. And you can tell it looks like it's approaching 1. You can even see it here. We're just clicking off more and more 9s. So if I were to add an extra 0 there, we'd probably just get more and more 9s. So it looks like it is converging. So now that is our next test. You can even see it going up here. These are all the individuals. So that's S sub 13 right there. That would be S sub 31. But these are our partial sums, and they're approaching something. So how do we find out what that is? So the one trick is to convert it into partial fractions and seeing if you have a telescoping series. So first thing we want to do, though, is write this. So we got to change it to a 1. So we can put the n here. Change it into our partial sum right there. And then after that, we can say the limit as n approaches infinity of our S sub n, and then see if there is a limit that it's converging to, which we already know there is. So partial fractions, that's the best thing to use when we have these. If we were to plug it in right now, don't write this, we'd have 1 over 1 times 2, plus 1 over 2 times 3, plus 1 over 3 times 4. So we're not really seeing it. It's a nice pattern, but we're not seeing any cancellations or anything to make us be able to write some formula for S sub n so we can take the limit of it. So if we use partial fractions, we say a over I plus b over I plus 1, and then we could say a times I plus 1, b times I, and we use our partial fractions. So ai plus a and bi, and these have to add up to a numerator of 1. So that would mean our a is 1, because there is no I. And a plus b would have to be 0, meaning b is negative 1. So now if we plug those in, we get the sum from I equals 1 to n of 1 over I minus, and that's what I was looking for, 1 over I plus 1. So now if we plug this in, we end up with this. This is 1 over 1 minus 1 over 2 plus, and now that, so you see this would be our I equals 1. And so now we're dealing with I equals 2. And so that would be 1 over 2 minus 1 over 3. And you can already see there's a cancellation. Boom, boom. And so that's what we're looking for. We want to get all those middle elements to cancel so that we can get a nice formula for this. All right, so the next then obviously would be 1 over 3 minus 1 over 4. That's our pattern. And this would continue all the way to the very end. And I always want to look at the term right before that last one. So we want to look at n minus 1 and then at n. So this way we end up with this. This would be 1 over n minus 1. If we plug that n minus 1 in here, we get n minus 1. Plugging n minus 1 in here, the 1 and the minus 1 would cancel, giving us just 1 over n. Plus, and then the last one is just literally plugging it back in, like that. And you can see that was the cancellation I wanted. So since those are canceling, we know everything in the middle is also canceling, giving us 1 minus that. So we end up with 1 minus 1 over n plus 1. So the sum, right, our partial sum to n is 1 over 1 n plus 1. So you could just plug in any number now. So if I were to plug in 1, this would be my formula. Plug in 2, that's my formula. 3, that's my formula, and so on. So we could find the sum up to any value we want, and we want to go to infinity. So now we plug it in here, and we use our limit rules. So that's 0 because the denominator is bigger, and we get 1. And so that's what we should be getting up here. And you can see that's what it's approaching. So if I add an extra 0 here, you can see it's just going to keep clicking on more 9s. And so our limit is 1. All right, well, this also works the other way. So if we have the sum as n approaches 1 of infinity, we can make our general term. So I equals 1 to n of I plus 1. And we can use our rules. So this is I equals 1 to n of I. So our summation properties. And so this would become n plus 1 over 2. That's our formula for I. Plus, and then that's just going to be n times 1. So it's n. So now we can say this is the limit as n approaches infinity. And we'll call this our s sub n, because that's what it is, of s sub n, which is the limit as n approaches infinity of n plus 1 over 2 plus n. And I don't have to even add those together. We know that's a polynomial. So this goes off to infinity, which means it diverges. And this one converges. So that's all you're using it for. Different rules, different tricks. And again, if you use Desmos to verify this, I'll hit play. You can see you've got it plugged in right here. It's just going off to infinity. Look at it. It's getting bigger, bigger, and bigger because we're just adding. You can even see that here. If I plug in 1, I get 2. I plug in 2, I get 3, and then I get 4 and 5 and 6. So I'm just going to keep adding numbers off to infinity. Nothing's canceling. Nothing's getting smaller. And then some of them you can just look at and know it's not going to go to anything. So I'll hit play here. And by plugging them in, you can see it's just going to alternate between 1 and 0 all the way down as we go. And if it's going to alternate between 1 and 0, its limit doesn't exist. It's not getting smaller. This one's not coming in and approaching this one, while this one comes up from the bottom, and they're just alternating around 0 and then becoming closer to 0. Or if this one would curve in to 1, and then they would just alternate very closer to 1 and went smaller and smaller. No, it's just going top, bottom, top, bottom, top, bottom. And so this one does not exist, which means it diverges. So the easiest thing to do when you see these alternating series, see up here, this one is telescoping. I don't know where the n came from. We get canceling. This one was just a polynomial, and it just goes off to infinity. And then this one just goes up and down. So if you were to plug it in, right, if we were to plug in n equals 1, that would be 2, which is even. So we're just looking at the exponent. So n equals 1 would be even, which would make that 1. The next term, though, now would be the 1 plus, now we're going to plug in 2 again, which would make that negative 1. And so you end up with 0. So we're just starting over. So if I plug in 1, I get 2, which is positive 1. And then I would plug in 2, which would give me 3, which is negative 1. So 1 minus 1 is 0. And then we'd start over, and it's 1, 0, 1. There's no convergence in sight. So this diverges just by looking at it. And there you go. So one of these methods is to write it as a partial sum and then take the limit of that partial sum. So if you can see that, converting that partial sum into a nice little formula that we can take the limit of, we can see if it converges or diverges that way.